Hello there, and welcome to the Sleepy Space channel. Every image of space you have ever seen has had the space taken out of it. The distances are too large to fit on any page, so illustrators keep the objects and discard the gaps, and what remains is a picture missing its dominant ingredient. An atom is 1,000 trillion parts empty, and so is the solar system. A spacecraft could cross the asteroid belt with its shutters closed and never come near a single object. A nebula is a better vacuum than anything we can build on Earth. Tonight we put the emptiness back in, one scale at a time, from the inside of a single atom out to the great voids where almost nothing lives at all. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But none of this is anything you need to carry tonight. The gaps have been there for billions of years, and they will still be there in the morning. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. Every picture of space is wrong. There is a quiet problem at the heart of every image of space ever made. It is not a problem of accuracy in the ordinary sense. The objects are drawn correctly. The colors are reasonable. The shapes match what the instruments record. The problem is that the space itself has been removed, and it has been removed so consistently, for so long, and by so many careful people, that almost nobody notices it is gone. The reason is simple, and it is a matter of geometry rather than intent. A picture has a fixed size. Within that size, an illustrator must show both the objects and the distances between them, and in space those two quantities are separated by factors so large that no page, no screen, and no printed diagram can hold them at once. If the planets are drawn large enough to recognize, the distances must be crushed down to a fraction of their true value. If the distances are drawn correctly, the planets shrink below the resolution of the paper and disappear entirely. Faced with that choice, every publisher, every textbook, every documentary, and every space agency has made the same decision. They keep the objects. They discard the space. And the result is that essentially every image any of us has ever seen of the solar system, of an asteroid field, of a glowing nebula, or of a cluster of galaxies, is a compression. Not a falsehood exactly. A picture with its dominant ingredient quietly taken out. The compression is made worse by something else, which is that telescopes point at things. Missions are sent to things. Photographs are taken of things. There has never been a published photograph of an empty cubic light year, because there would be nothing in the frame and no reason at all to print it. So the entire visual record of the universe is a catalogue of its rarest and densest features, gathered together and presented as though it were a fair sample of what is out there. It is a little like judging the surface of the Earth from a collection of photographs of mountains. Even the night sky performs the same trick, without any help from an illustrator. Look up on a clear night and the stars appear crowded, laid across the dark in overlapping drifts. But the eye records only direction. It has no way to register distance. Two stars that appear to sit side by side in a constellation may be separated by thousands of light years, one of them near and faint, the other enormous and impossibly far. The sky flattens all of them onto a single dome, and the crowding is entirely an artifact of that flattening. There is no crowd. There is a very thin scattering of objects at wildly different depths, painted onto the inside of a shell by an eye that cannot tell them apart. Photography adds its own layers. A nebula that requires hours of accumulated exposure to register as a bright cloud is presented as though a passing traveler would see it that way. Color in deep space imagery is very often assigned rather than observed, mapping wavelengths the eye cannot detect onto the narrow band it can. There is nothing dishonest in any of this. It is how faint things are made visible at all. But the habit of assigning color quietly reinforces the habit of assigning substance, and the finished image carries a solidity that the original object never had. And beneath a great many of these pictures sits a small phrase that says more than it appears to. Artist's impression. The artist's task, in those cases, is to make emptiness interesting, and there is only one way to do that. You fill it. The closest thing to an honest photograph of emptiness is the deep field. Astronomers occasionally choose a patch of sky that appears entirely blank, a piece of dark no wider than a grain of sand held at arm's length, and hold a telescope on it for days. The exercise exists precisely to test whether blank sky is blank. It is not, and the images that come back are among the most reproduced in astronomy. But it is worth noticing what those images actually prove. The patch filled up only because the exposure reached outward across billions of light-years to find its contents. Foreground emptiness is not photographable. It can only be crossed. There is one form of illustration that does tell the truth, and it works by refusing to fit on a page at all. A scale model walk lays the solar system out across a town at one fixed ratio, with no cheating in either direction. The sun goes in a park. The inner planets go in the next street. The outer ones go a kilometer or more away, in car parks and playing fields, and the yards of houses whose owners have no idea what has been placed there. The models exist because a diagram cannot do the job, and walking one is the only common experience most people ever have of the true proportions. It is worth adding that the same distortion runs in the other direction as well. The familiar diagram of an atom, a small dense center with particles arranged around it at a comfortable distance, carries exactly the same compression as the familiar diagram of a solar system, and for exactly the same reason. That is why the two pictures look so alike. The resemblance has misled generations of people in both directions at once, and it is the reason the next part of this begins not with the stars, but with something much closer to hand. So the correction this evening makes is a simple one, and it can be stated plainly at the start and then demonstrated, patiently, for the next 2 hours. Matter is the exception. Emptiness is the ordinary condition of the universe, at every scale from the inside of a single atom to the gaps between clusters of galaxies. And the ratio between the two is not close. It is not 2 to 1, or 100 to 1, or even 1,000,000 to 1. In most places it runs to many trillions to 1, and in the largest and emptiest regions it runs far beyond that. There is one measurement that makes this easy to follow, and it is worth carrying through the whole night, because it will be the thread that ties the 10 parts of this together. The measurement is simply the number of particles in a cubic centimeter, a volume about the size of a sugar cube. Count how many atoms or molecules sit inside that small box, and you have a single honest number for how full or empty any given place in the universe actually is. Begin at home. The air in an ordinary room at sea level holds roughly 25 quintillion molecules in every cubic centimeter. Written out, that is a 2 and a 5, followed by 18 more digits. This is the density we evolved inside, the density our intuitions are calibrated to, and it is by a very wide margin the fullest environment in this entire episode. Every other number tonight will be smaller. Most of them will be smaller by amounts that are difficult to hold in the mind. The first step down is the emptiest place human beings have ever managed to create. Inside a laboratory vacuum chamber, pumped and baked and cooled for days, the density can be driven down to something on the order of 1,000 particles per cubic centimeter. That is a reduction by a factor of 10,000 million from the air outside the chamber walls. It requires steel and pumps and patience, and it works only inside a small sealed volume. It represents the outer limit of what careful engineering can achieve on the surface of a planet. The next step down is the space between the planets. Out where the Earth orbits, the thin outflow of particles streaming from the Sun arrives at a density of roughly 5 particles per cubic centimeter. Not 5,000. 5. Ordinary interplanetary space, inside the warm inner solar system, in the middle of the busiest region of the Sun's territory, is already 200 times emptier than the finest vacuum we know how to build. Beyond the reach of that solar wind lies the space between the stars, and there the number falls again, to something in the region of 1 atom per cubic centimeter across the galaxy as a whole. Locally, it is thinner still. The Sun currently sits inside a cavity a few hundred light-years across, hollowed out long ago by the expanding shells of stars that died, and inside that cavity the density drops to about 1 atom in every 20 cubic centimeters. A thimble of interstellar space, out where we are, contains a handful of atoms and nothing else. Then comes the space between the galaxies, and here the ladder takes its steepest step. Intergalactic space holds something on the order of 1 atom per cubic meter. A cubic meter is 1,000,000 cubic centimeters, so this is 1,000,000th of the density of the space between stars, and it is the condition of the overwhelming majority of the volume of the universe. To gather a single gram of ordinary matter out of it, you would need to sweep clean a volume the size of a mountain. And then, finally, the great voids, the enormous rounded emptinesses between the filaments of galaxies, hundreds of millions of light-years across, where the density falls by another order of magnitude or more, and where a galaxy sitting at the center would find nothing else within 100 million light-years in any direction. Take everything in the universe at once. Every star, every planet, every grain of dust, every atom of hot gas, and all of the unseen material that outweighs all of it several times over. Smear the entire inventory perfectly evenly across all of space, leaving no lumps anywhere. The result is a density of about 6 hydrogen atoms worth of mass in every cubic meter. Restrict the count to ordinary atoms alone, the kind that make up stars and planets and people, and the average comes to roughly 1 atom in every 4 cubic meters, 1 atom, on average, in a volume rather larger than a bathtub. That is the honest texture of the universe. Not the crowded field of the illustrations. Not the banked luminous cloud of the photographs. A few atoms in a small room, and almost everywhere, nothing at all. Over the next 2 hours, we will walk down that ladder 1 rung at a time, and at each rung, we will take a familiar picture and put the missing space back into it. We will start inside the atom, which is emptier than the solar system. We will pass through the asteroid belt, which is almost impossible to hit anything in. We will fly through a nebula and notice nothing. We will find that stars are the loneliest objects in existence, and that galaxies, by comparison, are practically neighbors. We will end in the voids, and then we will do one last thing, which is to put back the few remarkable things that genuinely do fill empty space, and which do not happen to be made of matter at all. None of this is a correction anyone needs to feel troubled by. The pictures were never intended as measurements. They were made to show what is there, and they do that well. They simply cannot show how much of everything else there is, and so, for most of us, the space in space has quietly gone missing. Tonight, we put it back. Part 2. The emptiness inside matter. Before there is emptiness between things, there is emptiness inside them. This is the part of the story that is closest to hand, and in some ways the strangest, because it does not concern anything distant at all. It concerns the surface you are resting on right now. An atom is built around a nucleus, and the nucleus is where essentially all of the mass lives. Protons and neutrons, bound together in a tight cluster, account for something like 99.9% of everything the atom weighs. But that cluster is very small. A nucleus measures somewhere between 1 and a few femtometers across, a femtometer being a millionth of a billionth of a meter. The atom as a whole, measured out to the edge of its electrons, measures around a tenth of a nanometer. That is roughly 100,000 times wider. A factor of 100,000 in width does not stay a factor of 100,000 when you move to volume. Volume grows as the cube of length, so the ratio becomes 100,000 multiplied by itself 3 times over, a factor of about 1,000 trillion. By volume, then, an atom is somewhere in the region of 99.99999999999% empty. The mass is all in one tiny knot at the center, and the rest of the atom is space. The standard illustration is worth keeping because it is the only way to make that ratio sit still in the mind. Take a single atom and enlarge it until the nucleus is the size of a grain of rice, and place that grain of rice at the center of a large sports stadium. On that scale, the electrons belong somewhere out among the seats in the upper tiers. Everything between the grain and the seating, the whole bowl of the stadium, every row, all that air, is the interior of the atom, and it holds no matter of the ordinary kind at all. We know this because of how it was discovered, and the discovery has an appealing shape. A thin sheet of metal foil was placed in the path of a stream of fast, heavy particles, and the expectation was that the foil would deflect them all a little, the way a fog deflects a beam of light. Instead, almost every particle went straight through, as though the foil were not there. Only a tiny fraction were turned sharply aside. It was the emptiness that was the result. The rare, hard deflection was the surprise, the first sign that the mass of matter was concentrated in something very small and very dense, with nothing much in between. Which leads directly to the question anyone asks next. If matter is 1,000 trillion parts nothing, why does a table stop a hand? The answer is that solidity has never been a matter of substance meeting substance. When a hand rests on a table, no part of the hand touches any part of the table in the sense we imagine. What happens is that the outer electrons of the atoms in the hand approach the outer electrons of the atoms in the table, and two things resist. The first is ordinary electrical repulsion, since both sets of electrons carry the same charge and push each other away. The second is deeper and stranger, a rule of quantum mechanics that forbids identical particles from occupying the same state. Crowding them together costs energy, and the cost rises steeply the closer they come. So firmness is a force, not a fullness. The floor holds you up because of a rule, not because of a wall. Everything in a room is a lattice of tiny, dense knots, held apart at enormous relative distances by fields that will not let them approach, and the whole arrangement feels solid because the fields are very strong, and the distances, on our scale, are very small. There is an important qualification here, and it deserves to be said gently rather than as a correction. When we say the atom is empty, we mean empty of nuclei and of the heavy particles inside them. We do not mean empty of everything. The electron is not a small ball orbiting at a distance with vacuum on either side of it. It is a standing pattern of probability that fills the entire atomic volume, a kind of smeared presence with no sharp edge and no measurable size of its own. Every experiment ever performed to find the electron's diameter has returned an upper limit and no lower one. It behaves, as far as anyone can measure, as a point. And the space inside the atom is thick with field. The electric field of the nucleus reaches all the way out and beyond. So the emptiness is real, but it is an emptiness of stuff, rather than an emptiness of structure. That distinction is going to recur at every scale for the rest of this evening, and it will return in full at the very end. There is a reason atoms bother to be so large in the first place, and it is not arbitrary. Confining a particle to a smaller region costs energy. The tighter the confinement, the higher the price. An electron squeezed close to the nucleus would carry an enormous energy of confinement, and that cost pushes outward against the electrical attraction pulling it in. The atom settles at the size where those two effects balance. Atoms are big because being small is expensive. The emptiness inside matter is not a gap that something forgot to fill. It is the shape of a negotiation. The consequence of all this is that ordinary matter can, in principle, be compressed by amounts that sound impossible, and in several places in the universe it has been. Begin with a small illustration. Every human being alive is made of atoms that are, by volume, essentially all empty space. Remove that space entirely, collapse every atom in every body down until the nuclei are touching, and the entire human species, all 8 billion of us, would occupy a volume roughly the size of a sugar cube. Not one person, all of them. The mass would be unchanged. Only the emptiness would be gone. Nuclear matter, packed that tightly, reaches a density of around 200,000 trillion kilograms per cubic meter. A teaspoon of it would weigh about 1 billion tons. At that density, the entire Earth would form a sphere a few hundred meters across, small enough to sit inside a city park. The Sun, with its third of 1 million Earth masses, would form a ball roughly 20 kilometers wide. And this is not merely a thought exercise, because the universe performs it. When a massive star exhausts its fuel and its core collapses, the electrons are driven into the protons, atomic structure fails completely, and what remains is a sphere of nuclear matter about the width of a city, holding more than the mass of the Sun. A neutron star is precisely what matter looks like once the empty space has been taken out of it. There is an intermediate stage as well, which is worth a moment. In a white dwarf, the remnant left when a smaller star like our own runs down, the electrons have been squeezed together tightly, but the nuclei have not yet been forced to touch. The result is a density of around 1 ton per cubic centimeter. A sugar cube of white dwarf material would weigh about as much as a small car. The star is holding itself up entirely with the same rule that keeps your hand from passing through the table, and when that rule finally gives way in a heavier object, there is nothing left to stop the collapse at all. There is a neat symmetry in this. The same rule that makes a floor solid is the rule that holds up a white dwarf against its own weight, and the rule that holds up a neutron star against a weight far greater still. It is one principle, operating at 3 enormously different scales, and it has a limit. Pile on enough mass, and even that resistance is overwhelmed, and there is nothing left in physics to halt the collapse. What forms then is a black hole, which is simply the outcome of the last defense of emptiness giving way. Nuclear matter is also very nearly incompressible, which produces a curious result. Neutron stars vary considerably in mass, and yet they vary hardly at all in size. Add half a sun's worth of material to one, and it barely widens. Once the empty space has been removed from matter, there is very little left to take. The emptiness of atoms also has a quieter consequence, which is that some things simply pass through matter as though it were not there. Neutrinos interact so weakly, and matter offers so little to interact with, that trillions of them pass through every human body every second, without leaving any trace whatsoever. A neutrino could travel through a light year of solid lead, with a reasonable chance of emerging on the far side untouched. From the neutrino's point of view, a planet is a very thin fog, and the emptiness goes further down than the atom. The protons and neutrons in the nucleus are themselves mostly unoccupied by the same logic. The quarks within them are confined to a region far smaller than the particle they compose. Stranger still, those quarks account for only a small fraction of the particle's mass. Almost all of the weight of a proton comes from the energy of the field binding it together, rather than from the particles inside. Which means that the great majority of the mass of your body is not matter in any everyday sense. It is binding energy, held in a structure that is almost entirely empty at every level you care to examine. So the chair holds, the floor holds, the page holds. And all of it is 1,000 trillion parts nothing, arranged carefully enough and held apart firmly enough to feel like the most reliable thing in the world. Once that has settled, the emptiness of the sky stops sounding like an exotic claim about somewhere far away. It begins to sound like a continuation of something that was already true in the room. Part 3. The real proportions of the solar system. The diagram everyone learns from shows a sun on the left and a row of planets marching away to the right at pleasant, regular intervals. It is a good diagram for learning names and order. It is, in every other respect, a work of fiction. At true proportions, that page would be blank, with a small dot near one edge and nothing else visible anywhere on it. So the honest version has to be built at walking scale, and the standard model begins with a piece of fruit. Shrink the sun until it is a grapefruit, about 14 centimeters across, and set it down on the ground. On that scale, every distance in the solar system divides by 10,000 million. The Earth becomes a coarse grain of sand, a little over a millimeter wide. And that grain sits 15 meters away from the grapefruit, the length of a bus, or the width of a small garden. Everything that has ever happened in the history of life, every ocean and every continent, every city and every war, takes place on a grain of sand, a bus length from a piece of fruit. Keep walking. Mars is a smaller grain at about 23 meters. The asteroid belt begins somewhere past 30. Jupiter, the largest planet by an enormous margin, is a marble 1.5 centimeters across, and it lies 78 meters from the grapefruit, most of the length of a football pitch. Saturn is another marble at 140 meters. Uranus is a peppercorn at nearly 300. And Neptune, the outermost planet, is a peppercorn 450 meters away, most of the way around a running track. Now the number that gives the model its point. On that same scale, the Sun as a grapefruit, the Earth as a grain of sand 15 meters off, the nearest other star is another grapefruit, and it sits 4,000 kilometers away. Not 400 meters, 4,000 kilometers. A continent away, across an ocean, in another country. That is the true ratio between the size of a solar system and the space it floats in. The lesson of the model is not that the planets are small, although they are. It is that the solar system is not really a collection of worlds at all. It is a volume of nothing, with a star at the center and a scattering of specks distributed through it at intervals that no page can honestly show. The arithmetic makes this exact. Take the sphere of space out to Neptune's orbit and calculate its volume. Then add together the volumes of every planet, every moon, every asteroid, and every comet inside it, everything solid the system contains. The fraction comes out at a few parts in 1,000 trillion. That number should sound familiar, because it is very nearly the same ratio we found inside the atom. The solar system and the atom are empty to almost exactly the same degree. The old diagram that drew them as versions of one another was wrong about the physics, but it was accidentally right about the proportions, and it was wrong about those proportions in both pictures at once. Mass tells the same story in a different currency. The Sun holds about 99.86% of all the mass in the solar system. Jupiter holds roughly 2/3 of the small remainder. Everything else, Saturn, Neptune, Uranus, the Earth, Venus, Mars, Mercury, every moon, every asteroid, every comet, every grain of dust, together amounts to well under 1/20th of 1%. The solar system is a star, a modest lump beside it, and rounding error. There is a second way to feel these distances, and it is the one worth carrying, because it converts space into time, and time is something a body understands. Light is the fastest thing there is. It crosses the entire Earth in a small fraction of a second, 7 times around the equator, while a sentence is spoken. From the Sun, it takes about 8 minutes and 20 seconds to reach us, which means that sunlight arriving now left before you sat down. It takes roughly 43 minutes to reach the orbit of Jupiter. It takes about 4 hours to reach Neptune. And to reach the most distant spacecraft still operating, out past 160 times the Earth's distance from the Sun, its signals take the better part of a day. Sit with that pairing for a moment. That spacecraft has been traveling continuously for decades, faster than any vehicle ever built to carry people, never stopping and never slowing. And the distance it has covered in all that time is a distance light crosses before the day is out. It is still, by any reasonable measure, in the immediate neighborhood. The delay is not merely a curiosity. It changes the nature of everything done at a distance. A vehicle on the surface of Mars cannot be driven, in the sense that anything on Earth is driven, because a message to it takes somewhere between about 8 minutes and over 40 to arrive, depending on where the 2 planets happen to sit in their orbits, and the reply takes as long again. By the time an operator sees a hazard, the vehicle has been sitting beside it for a quarter of an hour or more. So the machines are given instructions for the day and left to carry them out alone. Every rover that has ever crossed that ground has done so by itself. The emptiness makes conversation impossible, and so it makes independence compulsory. It is worth pausing on how little of the model human beings have visited. Return to the grapefruit and the grain of sand 15 meters away. Every crude spaceflight in history, every station, every capsule, every voyage to the moon and back, fits within a few centimeters of that grain. On a model that stretches nearly half a kilometer to Neptune and 4,000 kilometers to the next star, the entire human presence in space occupies a space about the width of a fingernail. Everything else we know of the solar system, we know from machines we sent out and never brought home. The emptiness also sets the terms of everything we are able to do out there, which is the point at which it stops being an abstraction. Missions to the outer planets do not carry the fuel to make the journey directly, because that fuel would weigh more than any rocket could lift. Instead, they borrow. A spacecraft is aimed at a planet, falls toward it, swings around it, and leaves in a different direction, carrying a little of that planet's orbital momentum away with it. Gravity assists exist because the gaps are so expensive to cross that we send our machines the long way round to avoid paying for them. The plane of the system deserves a mention as well, because it makes the emptiness worse rather than better. The planets do not orbit in random directions. They all travel within a few degrees of a common flat disk, a legacy of the spinning cloud they formed from. The asteroids and the outer icy bodies broadly follow that same plane, which means the solar system is not a sphere sparsely filled. It is a very thin disk sparsely filled, floating inside a much larger sphere that contains essentially nothing at all. Look up out of the plane, or down through it, and there is no material of any kind for an extraordinarily long way. And the emptiness deepens smoothly with distance, without any boundary to mark it. The solar wind streaming out from the Sun thins with the square of distance, so interplanetary space at Neptune is already far more rarefied than interplanetary space at Earth, long before the Sun's influence ends at all. Eventually that outflow slows, piles up, and gives way to the gas between the stars. The boundary where this happens is not a wall. Both spacecraft that have crossed it registered a change in the character of the emptiness, rather than in the amount of it, a shift in which particles were present, not a shift from something to nothing. There is a quiet detail in that crossing worth keeping. When a spacecraft passes out of the Sun's bubble, the density of particles does not fall. It rises. The solar wind has thinned so much by that distance that the gas of interstellar space, itself one of the emptiest environments in existence, is denser than the outflow it replaces. The Sun's great protective bubble is, at its outer edge, emptier than the emptiness it is holding back. And even that is not the edge of the Sun's territory. Far beyond it, thousands of times further out than Neptune, a vast shell of icy bodies is thought to surround the whole system, extending outward towards something like a light year. Those objects are so widely separated that the shell has never been seen as a structure, only inferred from the long-period comets that occasionally fall inward from it. If Neptune's orbit is a running track, the outer edge of the Sun's gravitational reach is thousands of kilometers away, and it is emptier there than anywhere else the Sun still claims. The bodies out there are so widely spaced that the shell has no shape anyone could point to. If a comet from that region is falling toward us tonight, the nearest object to it is likely to be further away than Neptune is from the Sun. Each one falls alone, in a dark so complete that the Sun itself is only a bright star among the others, which gives a strange final proportion for this part. The distance from the Sun to Neptune is about 4 light hours. The distance from the Sun to the next star is about 4 light years. The two numbers use the same digit and differ by a factor of roughly 9,000. Everything we call the solar system, every world, every mission, every photograph ever taken from within it, happens inside the first small fraction of 1% of the distance to our nearest neighbor. At the walking scale, one last time, the grapefruit in the park, the sand grain 15 meters off, the peppercorn at the far end of the track. And then 4,000 kilometers of nothing before the next grapefruit. That is not a system with gaps in it. That is a gap with a system in one corner. Part 4. The belt that is not a belt. Of all the pictures that have quietly misinformed us, none has traveled further from the truth than the asteroid field. In the picture, a ship weaves frantically between tumbling boulders that crowd the frame from edge to edge, and the danger is obvious. In reality, the asteroid belt is the emptiest crowded thing in the solar system, and crossing it is among the safest ordinary maneuvers there is. The population is genuinely large. The main belt contains well over 1 million bodies, more than 1 kilometer across, and many millions more below that size, down through boulders and pebbles and dust. If you were counting objects alone, it would be the busiest region between the Sun and Neptune. But the counting has to include the container. The belt occupies a broad ring of space, beginning at roughly twice the Earth's distance from the Sun, and extending out past 3 times that distance. It is more than 200 million kilometers across from inner edge to outer, and comparably deep, because the asteroids are not confined to a thin sheet. Their orbits are tilted, some by 20 or 30 degrees from the common plane, so the population is smeared through a torus of genuinely enormous volume. Divide the objects into the space, and the answer settles the matter. The typical distance between neighboring bodies of any appreciable size runs into the hundreds of thousands, and often the millions of kilometers. That is comparable to, and frequently greater than, the distance from the Earth to the Moon. Standing on one asteroid, the nearest other asteroid would in most cases be invisible, not a looming shape overhead, but at best a faint point of light indistinguishable from a star. The practical consequence is written into the history of spaceflight. Every mission ever sent to the outer solar system has crossed the belt, and not one has ever been struck. More than a dozen spacecraft have made the passage. Collision risk is not a design driver. It is not what keeps mission planners awake. The genuine difficulty is the opposite one. When a mission wants to visit an asteroid, it must be aimed at that specific object with great precision, because finding one is hard, and encountering one by accident is essentially impossible. Put it in the plainest terms. A traveler could fly straight through the asteroid belt with the shutters closed, on almost any trajectory chosen at random, and pass all the way out the far side without ever coming within sight of a single object. The most famous obstacle course in the solar system is, in practice, an open road. The mass tells the same story from another direction. Gather every asteroid in the belt together into one body, and you would end up with something substantially smaller than the Moon, around 3% of the Moon's mass in total. And a single object, the largest one, accounts for roughly a third of that by itself. The rest of that million-strong population, all of it together, adds up to about 2% of a moon. This corrects a second misconception, which is that the belt is the wreckage of a planet that broke apart. It is not. It is material that was never allowed to become a planet in the first place. Jupiter, forming nearby and enormously more massive, kept the region permanently stirred, driving the local bodies into orbits that crossed each other at speeds too high for gentle accumulation. Instead of sticking together, they shattered. And most of the original material did not stay at all. Over the long history of the solar system, the great majority of it was flung outward or inward and lost entirely. What remains is a remnant of a remnant, spread through a volume it can never come close to filling. There is a subtle piece of evidence for how rare collisions have become, and it is written into the belt's own record. Long ago, when a large asteroid was shattered, its fragments were left traveling on very similar orbits. Those fragments still travel on similar orbits today. Astronomers can pick them out as families, groups of objects scattered around the belt that share a common composition and a common origin, identifiable hundreds of millions of years after the event that made them. The reason those families survive is that nothing has disturbed them. If the belt were anything like the picture, if objects were routinely meeting one another, the families would have been ground down and mixed into anonymity long ago. Instead, they persist, distinct and readable, like handwriting that has never been smudged. The clearest signature of the belt's emptiness is that its oldest accidents are still legible. There is even emptiness within that emptiness. At certain distances from the Sun, an asteroid's orbital period falls into a simple ratio with Jupiter's, completing 3 orbits for every one of Jupiter's, or 2 for every one. At those distances, the same gravitational nudge repeats in the same place, over and over, and it accumulates. Objects are gradually pushed out. The result is a set of narrow bands running through the belt that have been swept nearly clear, gaps inside a region that was already almost entirely gap. The belt is not even the whole of the asteroid population. Sharing Jupiter's orbit, 60 degrees ahead of the planet and 60 degrees behind it, are 2 further swarms held in place by the balance of gravity between Jupiter and the Sun. Together they are thought to be comparably numerous to the main belt, and they are spread through an even larger volume at even greater separations. They are among the most populous groups of objects in the solar system, and standing in the middle of one, you would see nothing at all. If the asteroid belt makes the point through absence, Saturn's rings make it through geometry, and they make it far more beautifully. The main ring system spans something close to 280,000 kilometers from inner edge to outer edge. It is one of the largest structures in the solar system that can be seen from Earth through a modest telescope, and it is the most recognizable object in the sky after the Moon. Its typical thickness is about 10 meters. That figure is not a misprint, and it deserves to be turned into something the mind can picture. Take a single sheet of paper, 1/10 of a millimeter thick. Scale it up until it is 10 meters thick, and the same scaling makes it nearly 3 kilometers wide. A sheet of paper 3 kilometers across, stretched flat, would have the same proportions as Saturn's rings. And even that sheet would be far too solid, because the rings are not a sheet at all. They are separated particles, from grains of dust up to boulders a few meters across, more than 95% water ice, orbiting individually with a great deal of vacuum between them. The whole system, gathered up, would make a small icy moon, and nothing more. The most spectacular structure in the solar system contains a vanishingly small fraction of the Moon's mass, spread across a disk wider than the distance from the Earth to the Moon and thinner than a house. And there is a proof of this that anyone can see, which is the part worth keeping. Twice during each of Saturn's long orbits, the plane of the rings turns edge-on to our line of sight. And when that happens, the rings vanish. The most photographed feature in the solar system, the thing that makes the planet instantly recognizable to a child, simply disappears from the sky, because seen from the side, there is not enough material in it to register at all. It has happened many times since telescopes were first turned that way, and each time the planet appears for a while as a bare, pale globe with nothing around it. It also means the rings are a very poor place to hide anything. Illustrations show a dense field of ice boulders stretching away in all directions, but a traveler drifting within the ring plane would find the nearest large particle some distance off, and the view outward would be mostly stars. The rings look solid from 100,000 kilometers away, for the same reason a nebula looks solid from 1,000 light-years away, and we will come to that reason shortly. Depth does the work that density cannot. The rings hold their remarkable flatness through a gentle mechanism. The particles are in constant, very slow collision with one another, bumping at speeds of centimeters per second, not kilometers. Any particle that wanders above or below the plane is knocked back into it. Over time, this settles the whole system into the thinnest structure of its size anywhere in the solar system, maintained not by rigidity, but by the endless soft correction of the traffic. The visible divisions within the rings work like the gaps in the asteroid belt. They are cleared by resonances with Saturn's moons, and in the narrower cases, by small moons embedded in the ring system itself, sweeping their own lanes clear and holding the ragged edges in place. There is one more quiet fact about the rings, which is that they appear to be temporary. They are thought to be far younger than the planet, and material is slowly raining down out of them into Saturn's atmosphere. The rings are not a permanent feature of the solar system, but a passing one, and we happen to be here during the interval in which they exist. The other giant planets have rings as well, and their faintness is the last measure of how little material these structures require. They are narrow, dark, dusty bands, and they went entirely unnoticed for centuries. Some were found only when a planet passed in front of a star, and the starlight flickered briefly before and after the planet itself blocked it, proof of thin rings detected not by seeing them, but by watching something behind them dim. And further out, in the region beyond Neptune, the same pattern reaches its extreme. The icy bodies there are so widely separated that the typical distance between sizable objects exceeds the entire distance from the Earth to the Sun. It is called a belt. Nothing about it is belt-like. It is a very small number of very distant objects, moving slowly through a volume so large that the word for it has never really been suitable. Part 5. Clouds thinner than any vacuum we can build. A nebula in a photograph looks like weather. There are banks and towers of it, edges lit from within, dark lanes cutting across the bright regions the way storm cloud cuts across a sunset. It looks like something you could sail into. It looks, above all, like a substance. Here is what would actually happen if a spacecraft flew directly through the brightest nebula in the sky. Nothing. No thickening of the view. No haze gathering at the windows. No resistance, no buffeting, no color washing over the hull. The instruments would register a change, a modest rise in the particle count, a shift in the chemistry. The crew, looking out, would see the same stars they saw the day before. They would cross tens of light years of glowing cloud and never once be able to tell that they were inside it. The reason is the density. Even the brightest, densest emission nebulae, the ones that fill the famous photographs, hold only a few hundred to a few thousand particles in every cubic centimeter. Recall the number from the beginning of the evening. The air in an ordinary room holds about 25 quintillion. The difference is a factor of something like 10,000 million, which produces a sentence worth stating carefully, because it sounds like an exaggeration and is not. A nebula is a better vacuum than anything we know how to make. Take the finest laboratory chamber on Earth, pumped and baked and sealed with great effort, and its interior is still more crowded than the interior of a glowing cloud in space. The most beautiful structures in the sky are emptier than the emptiest boxes we have ever built. So the obvious question is how anything that thin manages to be seen at all across thousands of light years. The answer is depth. These structures are commonly tens of light years across. When a telescope looks at one, it is not looking at a surface. It is looking through the entire thickness of it at once, along a line of sight that runs for trillions upon trillions of kilometers. Almost nothing, stacked end to end for that distance, adds up to a very large number of atoms in total. Each one contributes a faint glow, and the glow accumulates along the line. That is the whole trick, and once it is understood, a great deal of the sky reorganizes itself. The brightness of a nebula is a total, not a concentration. It is the sum of an immense column of near vacuum, presented as though it were a surface. From outside, you see the sum. From inside, you are within the sum, contributing to it, surrounded by it, and able to see none of it, because at any point along the way there is essentially nothing beside you. There is an everyday version of this effect, and it is worth keeping because it makes the astronomy feel less exotic. Ordinary air is transparent. You can see through a room without noticing the air at all. But look along a valley on a clear day and the far hills are washed pale and blue, and look further, out to a mountain range 50 kilometers off, and the range is barely more than a silhouette. Nothing has changed about the air. Only the length of the column has changed. The atmosphere becomes visible when there is enough of it lined up, and a nebula is the same principle carried out to a length of 100,000 million kilometers. It is worth doing that arithmetic once, slowly. A nebula 24 light-years deep presents a line of sight roughly 230 million kilometers long. Even at a few hundred atoms per cubic centimeter, a column that long contains an astonishing quantity of material in total. And a traveler crossing it at the speed of a fast spacecraft would spend not hours or years, but many tens of thousands of years inside it, in a place that would look, at every moment of that crossing, exactly like ordinary empty space. A well-known example gives the numbers a home. One of the brightest star-forming regions visible from Earth measures roughly 24 light-years across and contains something on the order of 2,000 times the mass of the Sun in gas. That sounds substantial, and in total it is. But spread 2,000 suns worth of material through a volume 24 light-years wide, and the result is thinner than anything on this planet has ever been. The light itself has a specific origin, and it is not reflection in most cases. Inside these clouds, hot young stars pour out ultraviolet light, energetic enough to strip electrons away from hydrogen atoms. Out in the thin gas, those free electrons eventually find protons again and recombine, and as they settle, they release light at very particular wavelengths. The characteristic deep red of so many nebula photographs is the color of hydrogen atoms reassembling themselves, one at a time, across tens of light years of near emptiness. Not all nebulae work this way. Some do not emit at all, but merely scatter the light of nearby stars off their dust, which is why those take on the color of the star rather than the color of the gas, and tend toward blue. It is the same scattering that makes the daytime sky here blue, performed by grains rather than molecules, across light years rather than kilometers, and against a background of permanent night. The temperature of this material is worth a moment because it is where intuition fails most completely. The gas in a bright nebula is often at thousands of degrees. That sounds violent. It carries almost no heat at all. Temperature measures how fast individual particles are moving, while heat depends on how many particles there are to carry the energy. In a nebula, the particles are moving very fast, and there are almost none of them. A hand held in that gas would freeze rather than burn, radiating warmth away into the dark far faster than the sparse, fast atoms could deliver it. The dust makes the same point from the opposite direction. Interstellar dust accounts for only about 1% of the interstellar medium by mass, and the individual grains are minute, around 1/10 of a micrometer across, smaller than the particles in smoke. Their number density works out to roughly 1 grain in a volume the size of a large building, a cube perhaps 50 meters on a side, holding a single speck. And yet that dust is thick enough to hide the center of our own galaxy. The dark lanes that run along the band of the Milky Way on a clear summer night are not curtains and not clouds in any ordinary sense. They are the accumulated effect of 1 speck per building, repeated across tens of thousands of light years, until the light of 100 billion stars is extinguished entirely. Depth again, doing the work that density cannot. For a long time, those dark patches were catalogued as holes, genuine gaps in the distribution of the stars, places where the sky simply had fewer of them. It took time to establish that they were not absences, but obstructions, and the correction is a small version of the correction this whole evening is making. What looked like nothing was something. What looks like something is very nearly nothing. There is an elegant escape from that obscuration, and it is how the heart of our galaxy came to be mapped at all. Those dust grains block visible light effectively, but they are nearly transparent to infrared. Look at the galactic center in the right wavelengths and the veil thins to almost nothing, and the crowded core appears through it. The dust is opaque and negligible at the same time, depending entirely on which light you use to ask. The photographs deserve one more note, in fairness to them. A nebula that appears in an image as a wall of layered color has usually been assembled from hours of accumulated exposure, in wavelengths chosen to bring out particular elements, with those wavelengths then mapped onto colors the eye can see. The structures in the image are real. The gas is genuinely arranged that way. What the image cannot convey is that the whole arrangement is a suggestion painted in almost nothing, and that a traveler standing at any point within it would be standing in what looks and feels exactly like open space. The one genuine exception to all this thinness deserves its place at the end. Molecular clouds, the cold, dark regions where stars are actually born, are far denser than their surroundings, reaching thousands and in their cores millions of particles per cubic centimeter. By the standards of this episode, that is extraordinarily crowded. It is enough for gravity to overcome the pressure holding the gas apart, enough for the cloud to fragment and collapse, enough for stars to form. And even those cores, the densest gas anywhere in the galaxy outside the body of a star itself, remain a far better vacuum than any chamber on Earth. Which gives one of the quiet reframes of the night. Star formation is not what happens when matter gathers into something substantial. It is what happens when the universe manages, briefly and locally, to become slightly less empty than usual. And slightly less empty is still emptier than anything we can make. There is an irony in it worth resting on. Everything solid, every planet, every rock, every body that has ever walked on one, began in one of these clouds. The material of the Earth was once spread through a volume so thin that a traveler passing through it would have registered nothing at all. Density is not the normal state of matter. It is a temporary condition that matter falls into occasionally, under gravity, and then leaves again. At the other end of a star's life, the process reverses. A dying sun-like star sheds its outer layers into a shell that expands outward and thins as it goes, glowing for a few tens of thousands of years before dissolving entirely back into the interstellar medium. And the heaviest stars end by driving a shockwave outward that sweeps the surrounding gas into a thin shell and leaves a cavity behind it, a hollow of even lower density that can persist for millions of years afterward. The Sun, as it happens, is currently inside one of those cavities. We will come to it in a moment. Part 6. The space between the stars. Before going further out, it is worth gathering up what has been laid down so far, slowly, because the numbers have been arriving steadily and they are easier to carry when they are stacked in order. We began with the pictures, and with the reason every one of them is a compression. Scale and content cannot share a page, so the space is always the thing discarded. Then we went inside the atom and found it empty by a factor of about 1,000 trillion, with all the mass in a knot at the center and solidity supplied by a rule rather than by substance. Then we stepped out to the solar system and found the same ratio again, a sphere of nothing with a star in the middle, a sand grain 15 meters from a grapefruit, and 4,000 kilometers of dark before the next one. Then the asteroid belt, where 1,000,000 objects are spread so thinly that a traveler could cross it blind and never see one. Then Saturn's rings, 280,000 kilometers wide and 10 meters thick, a sheet of paper 3 kilometers across that vanishes entirely when seen edge-on. And then the nebulae, glowing clouds emptier than any vacuum we can build, visible only because we look through so much of them at once. Everything so far has taken place within the neighborhood of a single star. From here on, the gaps are of a different order. The space between the stars, averaged across the galaxy, holds about 1 atom in every cubic centimeter. 1 atom in a thimble. Overwhelmingly, it is hydrogen, with some helium, a trace of heavier elements, a thin scattering of dust, a weak magnetic field, and the occasional cosmic ray passing through at close to the speed of light. Locally, it is thinner still, because the Sun happens to be sitting inside a hole. A cavity roughly 300 light-years across surrounds us, blown clear long ago by the expanding shells of stars that died in this region over the last several million years. Inside that cavity, the density falls to something like 1 atom in every 20 cubic centimeters. The Sun is drifting through a slightly denser wisp within the hole, a small local cloud at a few tenths of an atom per cubic centimeter, but the broader neighborhood is emptier than the galactic average by a wide margin. We live in a bubble carved by the deaths of stars we never saw. Now the spacing of the stars themselves, which is the cleanest number of the evening. The Sun is about 1,400,000 kilometers across. The nearest star system lies about 4¼ light-years away, which is roughly 40 trillion kilometers. Divide one by the other, and the ratio comes out at approximately 30 million. Each star in this galaxy is separated from its nearest neighbor by something like 30 million times its own width. Bring that down to a scale a hand can hold. Shrink the Sun to a grain of sand a millimeter across. On that scale, the next grain of sand lies 30 kilometers away. Not 30 meters, not 300. 30 kilometers, a long walk, several hours, before you would reach the next particle of matter of any kind. And between them, nothing but a few atoms per thimble, arranged with no pattern at all. It is worth being careful with the unit, because a light-year is used so casually that it stops registering. A light-year is not a long distance in the way that a continent is a long distance. Light travels 300,000 kilometers every second. It crosses the width of a planet in a fraction of a heartbeat, reaches the Moon in a little over a second, and reaches the Sun in 8 minutes. Now let it run at that speed, without slowing, for an entire year. That is 1 light-year. And the nearest star is 4¼ of them away. An earlier evening was spent on what that crossing would actually mean for anything traveling at the speeds we are capable of, and the answer bears repeating gently here. The fastest object human beings have ever launched would need something in the region of tens of thousands of years to make the trip. Not tens of years, tens of thousands. And that is to the nearest star of all, the shortest possible interstellar journey, the one closest to home. There is something worth picturing in that crossing, and it is the opposite of what a film would show. There would be no sense of motion. Nothing would stream past the windows. The stars ahead would not grow visibly for centuries at a time. For the overwhelming majority of the journey, a traveler looking out would see a scene that had not changed at all since the day before, and would not change appreciably in a human lifetime. Interstellar travel, if it is ever done, will not feel like traveling. It will feel like being still, in a dark room, for a very long time. The wide account matches. In the solar neighborhood, the density of stars works out to roughly 1 star for every 250 cubic light-years. Within 10 light-years of the Sun, there are only about a dozen star systems in total, and most of those are dim red dwarfs, none of which can be seen from Earth without a telescope. The sky is full of stars, because we can see very far, not because there are many nearby. The medium between them has structure of its own, and the structure runs against intuition. Interstellar gas exists in distinct phases: cold, dense clouds, warm, neutral gas, warm, ionized gas, and a hot, tenuous phase at temperatures of 1,000,000 degrees or more. The phases occupy very different fractions of the galaxy. The cold, dense clouds hold much of the mass in a small share of the volume. The hot phase holds very little mass and fills a great deal of the room, which means that the majority of the space between the stars is occupied by the emptiest phase available. The galaxy's dominant environment, by volume, is its thinnest one. The arrangement is also temporary, which is easy to forget. Stars move relative to one another at tens of kilometers per second on their own orbits around the galactic center, and the constellations are a snapshot rather than a structure. The star that is nearest to us tonight has not always been the nearest, and will not remain so. Over a few 100,000 years, the whole near sky rearranges itself. And every so often, on that same timescale, another star passes close enough to disturb the outer edge of the Sun's comet shell, which sounds alarming until you notice the distance. Even at closest approach, in such an encounter, the two stars remain trillions of kilometers apart. A close pass between stars would be invisible to anyone standing on a planet around either of them, except as a slow brightening of one point of light over many thousands of years. Occasionally, something does cross between the stars and arrive here. A handful of objects have now been identified passing through the solar system on paths that show they came from elsewhere and are not returning. It is a demonstration that material does travel between star systems. It is also a measurement of how thinly that material is spread, because in all of recorded astronomy, only a very few have ever been caught. The rarity of the detections is the point. Cosmic rays make the same case in a different register. These are individual atomic nuclei, accelerated to very nearly the speed of light by shockwaves from exploded stars, traveling across the galaxy for millions of years. They carry enormous energy for their size. And they are counted one particle at a time, because that is the rate at which they arrive. The galaxy that contains all of this is itself a study in thinness. The disk of the Milky Way spans about 100,000 light-years and is roughly 1,000 light-years thick. That is a width-to-thickness ratio of 100:1, which makes the galaxy proportionally flatter than a compact disk and, in its outer regions, flatter still. Above and below the disk lies the stellar halo, a far more thinly populated sphere of ancient stars spread through a much larger volume. And beyond even that, lies the dark matter halo, extending further out again, containing most of the galaxy's mass and nothing whatsoever that can be seen. There is one place where stars genuinely do crowd together, and it is worth visiting for the sake of honesty. In the core of a globular cluster, an ancient, tightly bound ball of hundreds of thousands of stars, the density rises by a factor of thousands compared with the solar neighborhood. The night sky from a planet in such a core would be extraordinary, with thousands of stars bright enough to cast shadows. And even there, the typical separation between neighboring stars remains of the order of light months. Direct collisions still essentially never happen. The same is true at the very center of our own galaxy, where stars are packed more tightly than anywhere else in it and remain separated by more than 1,000 times their own diameters. The dust between the stars deserves one more mention here because it does something quietly significant. It reddens starlight in the same way that distant hills go pale, and the amount of reddening depends on how much of it the light has passed through. That makes the dust a measuring instrument. Astronomers read the reddening of a star to work out how far its light has traveled and how much material sat in the way, turning the emptiness itself into a ruler and using the small imperfection of the vacuum to map the vacuum. There is a practical consequence to all of this emptiness that is easy to overlook. A spacecraft crossing interstellar space encounters almost no resistance. There is no drag to speak of, no medium to push against or be slowed by. Whatever makes an interstellar journey difficult, it is not the material in the way. It is only the distance and the time and the energy required to cover them. The road is perfectly clear. It is simply extremely long. And here, at the midpoint of the night, is where the strangest turn in the whole story begins to appear. Stars are separated by roughly 30 million times their own diameter. Hold that number. In the next part, we will measure the distance between galaxies in exactly the same way, separation divided by size, and the answer will not be 30 million. It will not be 30,000. It will be a few dozen. By the standard of their own scale, galaxies are close neighbors. Stars are the loneliest large objects the universe contains. Part 7. Galaxies that pass straight through each other. Galaxy collisions carry the most violent name in astronomy and are, in practice, among the gentlest events it describes. When two galaxies merge, hundreds of billions of stars from one pass through hundreds of billions of stars from the other. And across the entire encounter, which unfolds over billions of years, the number of stars expected to actually strike one another is, for all practical purposes, none at all. The reason is the number we ended the last part with. Stars are separated from their neighbors by roughly 30 million times their own diameter. Firing one swarm of such widely spaced points through another swarm of such widely spaced points is like releasing two clouds of gnats at opposite ends of a continent and letting them drift through one another. The clouds interpenetrate completely. Every gnat passes through the other swarm, and not one of them meets another. The arithmetic behind that claim is straightforward enough to follow. A star presents a target, a disk 1 million or so kilometers wide. It also has a territory to itself, a region tens of trillions of kilometers across, in which it is the only star. The chance that another star, crossing that territory on a random path, happens to pass through the small disk at the center, rather than the enormous emptiness around it, is the ratio of those two areas. That ratio is a number with a great many zeros in front of it. Multiply it by the hundreds of billions of stars involved, and by the several passes a merger takes, and the expected number of collisions is still, comfortably, less than 1. This is worth sitting with, because it inverts the mental image entirely. Nothing crashes. Nothing shatters. Two galaxies pass through each other the way two thoughts pass through the same evening. What actually happens is gravitational, Orbits are stretched and rearranged, the stately spiral pattern is pulled apart, and the two populations slowly settle into one. It is a rearrangement, not a wreck. There is one component that does collide, and it is the gas. Between the stars, in both galaxies, lies the interstellar medium, thin, but continuous rather than point-like. Two clouds of gas cannot pass through one another the way two clouds of stars can. They meet, they shock, they compress, and they heat. And compressed gas is exactly the condition under which stars form. The brilliant knots and chains of blue light, visible in photographs of interacting galaxies, are not collisions. They are births, great waves of new stars, lit by the pressure of two galaxies' gas reservoirs running into each other. So the picture reverses one more time. The stars, which look solid, pass through untouched. The gas, which looks like nothing, is the only part dense enough to notice the impact. Our own galaxy is on course for exactly this. The nearest large spiral is approaching at something over 100 kilometers per second, and in roughly 4 billion years, the two will begin to merge. The process will take several 100 million years to complete. The two disks will pass through one another, separate, slow, and fall back together, possibly more than once, before settling. At the end, there will be one galaxy, elliptical rather than spiral, with the arms erased and the orderly rotation replaced by stars moving on randomized orbits in every direction. Every star in both galaxies will survive it. Not one is expected to be struck. Some will be flung out of the merged galaxy entirely into intergalactic space and will spend the remainder of their lives traveling alone with no galaxy around them at all. But nothing will collide. The Sun, if it were still burning at that point, would very likely find itself on a wider orbit further out, in a sky that no longer had a band of light across it, because from inside an elliptical galaxy there is no disk to see edge on, and the Milky Way as a visible feature of the night would simply be gone. Seen from the ground, if there were ground to stand on, the whole thing would be almost imperceptibly slow. The approaching galaxy is already visible from dark skies as a faint smudge. Over the coming billions of years it would grow, gradually, until it filled a large part of the sky as a great tilted oval of light, and it would take hundreds of millions of years to make each stage of that change. No generation would ever notice it moving. The most dramatic event in the history of our galaxy would present itself to anyone alive at any moment during it as a completely still night sky. The star formation that a merger triggers is intense and brief. A galaxy in the middle of such an encounter can produce new stars at tens of times its ordinary rate, lighting up as a burst of blue that stands out across billions of light years. But the burst consumes the very gas that feeds it, and once that reservoir is spent, there is nothing left to make stars from. This is a large part of why elliptical galaxies are red and quiet. They are not old in the sense of being tired. They are galaxies that used everything at once, long ago, and have had nothing to build with since. At the center of it, something slower will be happening. Each galaxy carries a supermassive black hole at its core, and when the two galaxies settle, those two objects begin to spiral toward one another. It is a process measured in hundreds of millions of years, and it ends with the two combining into one, the quietest possible conclusion to the largest merger the local universe has to offer. The stars themselves keep a record of all this. Because they survive intact, they carry their chemical composition unchanged through the entire encounter, and the composition of a star reflects the galaxy it formed in. So a merged galaxy contains two distinguishable populations, mixed together but still readable, billions of years afterward. Our own galaxy has already eaten several smaller ones, and their stars can still be picked out today by the way they move and by what they are made of. It is possible to identify the leftovers of a meal that took place before the Earth existed. The smaller encounters are happening now, continuously. Large galaxies do not merge with small ones so much as unravel them. A dwarf galaxy falling toward the Milky Way is stretched by tidal forces into a long stream of stars, wrapped around our galaxy in an enormous arc, its original shape entirely lost. At least one is being pulled apart in this way at the moment. These streams are among the most thinly populated structures known. Stars spread even more sparsely than in the disk they are being drawn into, drifting in single file across 100,000 light-years. The same principle scales up one level further, to clusters of galaxies, and there it produces one of the most striking observations in astronomy. When two great clusters collide, three things are present: the galaxies, the hot gas between them, and the dark matter that outweighs both. The galaxies pass through, because galaxies are widely spaced points. The dark matter passes through, because it barely interacts with anything, including itself. But the gas cannot pass through. It collides with itself, slows, and is left stranded in the middle, while the galaxies and the dark matter carry on out the far side. The result is a cluster whose ordinary matter has been separated from its mass, a direct demonstration made possible entirely by the fact that the visible objects are too sparse to touch and the invisible medium is not. There is a related observation about how galaxies behave in crowds, and it follows from the same asymmetry. When a smaller galaxy falls into a large cluster, it does not run into anything. But it does run through the hot gas filling the cluster, and that gas strips its own gas away, trailing it behind like smoke from a moving fire. Deprived of raw material, the galaxy stops forming stars and slowly fades to red. Galaxies in dense clusters are quieter than galaxies in open space, and the reason is not collision but exposure, a wind they cannot avoid because the medium, unlike the galaxies, is everywhere. And here, finally, is the inversion this evening has been building toward. The Milky Way is about 100,000 light-years across. Its nearest large neighbor lies about 2.5 million light-years away. Divide the separation by the size, exactly as we did for the stars, and the answer is roughly 25. 25 galaxy widths between one great spiral and the next. Stars sit 30 million widths apart. Galaxies sit a few dozen widths apart. Measured against their own scale, galaxies are more than 1 million times more crowded than the stars inside them. Take that seriously for a moment, because it undoes the impression every photograph has ever given. In images of galaxy groups, the galaxies look scattered across an ocean of dark. In images of star fields, the stars look packed shoulder to shoulder. The truth is the reverse of both. If you shrank a galaxy to the size of a dinner plate, its nearest neighbor would be a few meters away across the room, close enough to walk to. If you shrank a star to the size of a grain of sand, its nearest neighbor would be 30 kilometers off. Galaxies live in something resembling a community. Stars live in something closer to total isolation, tens of millions of times their own size from anything else, drifting in a medium so thin it is measured in single atoms per thimble. The most solitary large objects in the universe are the very things that fill the night sky, and they only look crowded because we cannot see how far away they are. There is a reason for this difference, and it is not an accident of arrangement. Galaxies are held in groups by gravity and by the dark matter that binds them, and they formed together out of the same regions of the early universe. Stars, by contrast, formed inside clouds that dispersed, and have been drifting apart ever since on their own separate orbits. The clusters that stars are born in almost all come undone within a few 100 million years. Galaxies stay together. Stars do not. Which is why the largest structures in the universe have neighbors, and the ones we can actually see with the naked eye have almost nothing at all. Part 8. The space between the galaxies. Every step down the ladder so far has been a large one. This is the largest. Between the stars, the density is about 1 atom per cubic centimeter. Between the galaxies, it is roughly 1 atom per cubic meter. A cubic meter contains 1,000,000 cubic centimeters, so the space between galaxies is about 1,000,000 times emptier than the space between stars, and the space between stars was already emptier than any vacuum this planet can produce. The number is easier to feel through what it would take to collect anything from it. To gather a single gram of ordinary matter out of intergalactic space, about the mass of a paperclip, you would need to sweep clean a volume comparable to a large mountain. Not a room, not a building. A mountain, emptied atom by atom, for a paperclip. And then the surprising part, which turns the whole picture around. That, almost nothing, is where most of the ordinary matter in the universe actually lives. Stars are not where the atoms are. All the stars in all the galaxies, added together, account for only a small percentage of the ordinary matter that exists. The great majority of it is not in stars, or planets, or dust, or anything that shines. It is diffuse ionized gas, strung out through the space between galaxies, spread so thinly and heated so highly that for a long time it could not be found at all. Much of it sits in a state described as warm-hot, temperatures of hundreds of thousands to several million degrees, hot enough that its atoms have been stripped of their electrons entirely. Gas that hot would ordinarily be brilliant. This gas is not, because there is so little of it in any given place that it emits almost nothing detectable. It is simultaneously among the hottest and among the least visible material in existence. For years, this produced a genuine problem in the accounting. The physics of the early universe predicts, quite precisely, how much ordinary matter should have been made. Astronomers went out and counted what could be seen: the stars, the galaxies, the gas in clusters, the clouds along lines of sight, and the total came up well short. A substantial fraction of the ordinary matter in the universe appeared to be missing. It was not missing. It was spread through the space between everything, in a state so thin and so hot that it had simply never been counted. The resolution of one of the larger discrepancies in modern astronomy was, in the end, that the universe keeps most of its atoms in the gaps. Finding it required an indirect approach, and the method is elegant. Choose a very distant, very bright object, a galaxy with an active center, blazing across billions of light years. Its light travels toward us through everything in between. Wherever it passes through a cloud of intergalactic gas, that gas absorbs a narrow slice of the light at wavelengths characteristic of its composition, its temperature, and its motion. By the time the light arrives, its spectrum is marked with a forest of fine, dark lines, each one the shadow of a place where the emptiness was, very briefly, slightly less empty. That is how the space between galaxies has been mapped, not by seeing it, but by reading the marks it leaves on light that has passed through it. The medium is invisible, and its record is not. Inside galaxy clusters, the same material is denser and hotter still, and there it does glow, in X-rays, filling the space between the member galaxies with a diffuse haze at tens of millions of degrees. And here the accounting produces one of the most quietly startling facts in astronomy. That gas, spread through the volume between the galaxies, outweighs all the stars in all of the cluster's galaxies combined by roughly a factor of several. Which means that the most massive visible component of a galaxy cluster is not the galaxies. It is the gas between them. When we look at an image of a cluster and see a scatter of bright ovals against black, we are looking at the minority component, drawn on top of the majority, which is not drawn at all. And even that is not the largest share. Dark matter outweighs the hot gas by roughly a further factor of 5. It cannot be seen at all in any wavelength, and its distribution is mapped only by the way its gravity bends the light of more distant objects passing by. A cluster of galaxies, honestly rendered, would be a vast smooth halo of invisible mass, filled with a glowing haze of invisible-to-the-eye gas, containing a few hundred small bright specks that we habitually call the object. The galaxies themselves occupy a vanishing fraction of the volume. Even in a rich cluster, packed as tightly as galaxies ever pack, the space they physically fill is a tiny share of the space they inhabit. The largest clusters contain 1,000 galaxies or more, gathered within a region perhaps 20 or 30 million light-years across. That sounds like a dense assembly, and by cosmic standards it is the densest assembly there is. It is also, by any ordinary standard, almost entirely gap. 1,000 objects, each about 100,000 light-years wide, scattered through 30 million light-years of space, is not a crowd. It is a very sparse handful, in a very large room, and clusters hold one further quiet population that almost never appears in a photograph. Over billions of years, stars are pulled out of their home galaxies by the tidal forces of the encounters that build the cluster. Those stars do not fall into anything. They remain in the cluster, belonging to no galaxy at all, drifting through the space between them. Their combined light is a faint glow spread across the whole cluster, and in some cases it accounts for a substantial share of all the starlight in it. There are, in other words, entire populations of stars whose sky contains no galaxy, stars that live permanently in the gaps. It is worth noting what this does to the idea of an astronomical image. When a telescope observes a cluster in X-rays, the picture that comes back is a smooth, luminous cloud filling the whole field, and the galaxies are not in it at all. They are too cool and too small to register. When the same cluster is observed in visible light, the cloud disappears, and only the galaxies remain. Two images of the same object, taken at the same moment, showing entirely different things, neither of them showing the dark matter that outweighs both. The universe has to be assembled from several partial views, and none of the views includes the majority of what is there. Our own neighborhood is a modest version of the same arrangement. The local group spans roughly 10 million light-years and contains two dominant spirals, our galaxy and its nearest large neighbor, along with several dozen much smaller companions, most of them faint dwarfs, and a great deal of thin gas. It is not a crowd. It is two substantial objects and a scattering of small ones, distributed through a volume it is difficult to think about, held loosely together by gravity against the expansion of everything else. The two large spirals in it are about 2.5 million light-years apart, and each is about 100,000 light-years wide. Work out how much of the local group's volume is actually occupied by galaxies, counting generously, and the answer comes to a small fraction of 1%. The most substantial neighborhood we belong to is, like everything else this evening, essentially empty, and it is one of the fuller regions of the universe. Beyond the groups and clusters, there are galaxies that belong to nothing at all. Field galaxies sit alone, with no companions, nothing bound to them and nothing nearby, with millions of light-years of near-perfect vacuum in every direction. There are a great many of them. For such a galaxy, the sky at night would show only distant, unreachable smudges, and the nearest thing large enough to matter would be further away than the entire width of the local group. The medium between galaxies also has a history, which is worth a moment because it is one of the few things that has genuinely changed about emptiness over cosmic time. In the early universe, this gas was cool and neutral, and it filled everything as a uniform fog that light could not travel far through. Then the first stars and galaxies lit, and their ultraviolet light stripped the electrons from that hydrogen across the entire universe. The fog cleared. Light could cross open space, and it has been able to ever since. The transparency we take for granted, The fact that we can see anything at all at great distance is a property the universe acquired, rather than one it began with. Clusters are still being fed by that medium today. Long, thin streams of cooler gas run inward along the filaments of the cosmic web, delivering fresh material to the clusters at their intersections. These streams are the supply lines of the largest structures in the universe, and they consist of gas so thin that a person standing in one would be standing, by any measure available to the senses, in a perfect vacuum. Since then, gravity has been slowly organizing the medium, pulling it into sheets and filaments, compressing it and heating it as it falls. The gas between galaxies is hotter now than it has ever been, and more structured and thinner in the places it has drained away from. Which leads to the reframe this part exists to make. The bright objects are not the universe's contents. They are its condensations, the small fraction of material that gravity has managed to gather into something dense enough to shine. The medium is the normal state. Stars and galaxies are what happens at the rare points where the medium was allowed to collect. And when the full inventory is taken, the ordinary matter of that medium, the gas, the dust, the stars, the planets, everything made of atoms, accounts for about 5% of what the universe contains. Around 27% is dark matter. The remaining 68% is dark energy, which appears to be a property of empty space itself. Which is to say, nearly 7/10 of everything is a feature of the emptiness. We will come back to that at the end. Part 9. The voids, which are most of everything. At the largest scales anyone has been able to map, matter is not spread out evenly at all. Galaxies are not scattered through space like sand through water. They are arranged. They gather into long, thin filaments, thousands of galaxies strung end to end across hundreds of millions of light years. Those filaments spread out into flattened walls, and where filaments meet, the density rises into the great clusters. It is a structure with a name, the cosmic web, and it is the largest pattern the universe has. And in between all of it lie the voids, roughly spherical regions of near-total emptiness, 100 to 400 million light-years across, bounded by the filaments and containing almost nothing. The first thing to say about the voids is that they are not gaps between the interesting parts. They are the majority of the universe. Something on the order of 4/5 of all cosmic volume is void interior. The filaments and walls and clusters, everything with galaxies in it, everything that has ever been catalogued or photographed or named, occupy the remaining fifth. If the cosmic web is a sponge, the voids are the holes, and there is a great deal more hole than sponge. None of this was expected. For most of the history of astronomy, it was assumed that on large enough scales, the universe would smooth out, that if you stepped far enough back, galaxies would be spread through space with rough uniformity, like grain in a sack. The assumption was reasonable, and it was wrong. When the first large surveys began measuring distances to tens of thousands of galaxies and plotting them in 3 dimensions, the maps that came back did not show a scatter. They showed sheets and threads and great rounded absences, and the absences were the most conspicuous feature on the map. The universe turned out to be organized, and the organization turned out to be mostly emptiness. The scale of an individual void is difficult to hold. Take a well-mapped example, a roughly spherical region several 100 million light-years across, containing a few dozen galaxies where a region of that size would normally contain thousands. It was noticed as an absence, a place where the counts came back wrong and kept coming back wrong until it became clear that the region was genuinely almost empty rather than merely poorly surveyed. Consider what the sky would look like from a galaxy near the center of such a void. There would be stars, of course, the galaxy's own, filling the sky as ours do. But look outward, past them, and there would be nothing. No neighboring galaxies bright enough to see. No smudge of light on the horizon of the sky. Nothing near enough to interact with, nothing near enough to merge with, and nothing at all within 100 million light-years in any direction. Astronomers on such a world would have a considerably harder task than ours. Much of what we understand about the universe was learned from nearby galaxies, from watching them interact, from measuring their distances, from comparing their kinds. A civilization at the center of a void would have none of that within reach. They would see a single island of stars, and beyond it, an unbroken dark that ran further than any instrument they could build would easily cross. It is worth putting the crossing in terms of light, since that is the only thing that could attempt it. Light takes about 8 minutes to cross from the Sun to the Earth, 4¼ years to reach the nearest star, 100,000 years to cross our galaxy, and 2.5 million years to reach the neighboring one. To cross a single void, light needs something on the order of 300 million years. A beam that set out across one when the first dinosaurs were appearing would only now be arriving at the far side. And a void is not an unusually large feature of the universe. It is an ordinary one. There are a great many of them, packed against one another along the walls of the web, and each is a volume that light spends hundreds of millions of years traversing without passing anything at all. The voids are not perfectly empty, and it is worth being accurate about that. They contain thin tendrils and sheets of very faint galaxies, threading through the interior in a kind of ghost of the larger web. And they hold diffuse gas at a density of perhaps 1/10 of the cosmic average. Emptier than everything, but not nothing. What is most striking about them, though, is that they are not static. A void is actively emptying itself. Gravity works in both directions. As matter is pulled toward the filaments and walls, it is being pulled out of the interiors. The sparse material inside a void drifts steadily outward toward the surrounding structure, and the void grows emptier as the universe ages. So the gaps are not left over from anything. They are a process, still running. Every void in the universe is quietly widening and thinning tonight, and it will be more thoroughly empty tomorrow than it was yesterday. The galaxies that do live inside the voids are noticeably different from the rest, and the difference is instructive. They tend to be smaller, bluer, and richer in gas than galaxies of similar mass elsewhere. The reason is that they have grown up alone. Galaxies in groups and clusters are constantly disturbed, merged with, stripped, harassed, stirred. Void galaxies experience essentially none of that. They have been left to evolve at their own pace, slowly and without interruption, holding on to their gas because nothing has ever come along to take it. They are the universe's undisturbed cases, and they are studied precisely because so little has ever happened to them. The filaments themselves deserve a correction as well, because the word suggests something more substantial than it is. On a map of the cosmic web, the filaments are drawn as bright threads, and the picture invites the idea of solid struts holding the structure up. They are threads in the sense that a line of scattered dust is a thread. Relative to their length, they are extraordinarily thin, and the galaxies within them are separated by the same millions of light-years we have been discussing all evening. The web is a lattice of very fine, very sparse lines, drawn across a volume that is overwhelmingly interior. All of this grew from almost nothing. In the first moments of the universe, the distribution of matter was very nearly uniform, varying from place to place by only a few parts in 100,000. Those tiny variations were enough. Regions that began very slightly denser pulled in a little more material, which made them denser still, which pulled in more. Regions that began very slightly emptier gave material up and became emptier and gave up more. Over billions of years, gravity amplified a whisper of unevenness into the largest structures that exist. The voids and the clusters are the same original ripple, developed in opposite directions. Our own position in this arrangement is worth a mention. There is reasonable evidence that our galaxy sits within a large-scale region of below-average density, an underdensity spanning hundreds of millions of light-years, not a true void but a thinner-than-typical patch of the web. We appear to live somewhat toward the empty side of an already empty universe. And there is one open question in this territory that fits the evening's mood. In the ancient background radiation that fills the sky, there is a patch that is slightly colder than it ought to be, a large, faint, unexplained cool spot. One suggestion has been that an unusually large void lies between us and it, and that light passing through such a region loses a small amount of energy on the way. Whether that is the explanation remains unsettled. It is one of the things the universe has not yet told us, and it is a pleasant thought that the leading candidate for the coldest known patch of sky is simply an especially large amount of nothing. The voids leave a fainter mark as well, one that has been measured. Because the interior of a void is expanding a little faster than the universe as a whole, light passing through one arrives at the far side having lost a small amount of energy. It climbs into the region and coasts out of a shallower well than it entered. The effect is tiny, far too small to see in any single case. But averaged across many thousands of voids, it registers as a very slight cooling of the background light that has passed through them. The emptiness is measurable by its effect on what crosses it, which is the only way emptiness has ever been measurable at all. Even the largest structures are less solid than they appear. Superclusters, the enormous assemblies of clusters that the filaments build toward, are not gravitationally bound in the way that individual clusters are. They are being pulled apart by the expansion of space even as we name them. They are patterns rather than objects, and given enough time, most of them will dissolve. Which brings us to the number that the whole density ladder has been descending toward. Take everything the universe contains. Every star in every galaxy, every planet, every moon, every asteroid, every atom of hot gas in every cluster, every wisp in every void, and all of the dark matter that outweighs all of it several times over. Take the entire inventory and smear it perfectly evenly across all of space, leaving no clumps anywhere and no gaps. The result is a density of about 6 hydrogen atoms worth of mass in every cubic meter. Restrict the count to ordinary atoms, the kind stars and planets and bodies are made of, and the figure comes to roughly 1 atom in every 4 cubic meters. 1 atom, on average, in a volume the size of a small room. For comparison, the ground beneath your feet is about 10 to the 30th times denser than that. A number with 30 zeros after it, separating the average density of the universe from the average density of an ordinary rock. That is the honest texture of everything. Not the crowded star field, not the banked luminous cloud. 1 atom in a small room, almost everywhere, forever, with rare, tiny, extraordinary places where it gathered into something that could look around and count. Part 10. Emptiness is not nothing. We have spent 9 parts taking things out. It seems only fair to spend the last one putting a few back, carefully, and without undoing anything that has been established. Empty space is empty of atoms. It is not empty. Begin with light, because there is far more of it out there than there is matter. Every cubic centimeter of space in the universe, including the deepest interior of the emptiest void, contains around 400 photons left over from the first moments of everything. This is the background radiation, released when the universe cooled enough to become transparent, and it has been traveling ever since, stretched by expansion into faint microwaves. 400 photons in a sugar cube volume works out to 400 million in a cubic meter. Set that beside the number from the last part. Ordinary matter averages roughly 1 atom in every 4 cubic meters. Ancient light averages 400 million photons per cubic meter. By count, The emptiest place in existence contains something in the region of 1,000 million photons for every single atom. The void is not dark. It is saturated with the oldest light there is, at wavelengths no eye can register, everywhere, without exception. That light is also the most uniform thing known. Measure its temperature in one direction and then in the opposite direction, and the two agree to within a few parts in 100,000. The universe is enormously varied in its contents and extraordinarily even in its background, and the small unevenness that does exist is the whisper that grew into every filament and void we have been describing. Traveling alongside those photons, in comparable numbers, are neutrinos from the same era, something over 300 per cubic centimeter, everywhere. They have never been detected directly because they interact so weakly that no instrument has yet been able to register them. Their presence is inferred from the way their gravity shaped the growth of structure in the early universe. There are, at this moment, hundreds of them in every sugar cube volume of the room you are sitting in, and there is no experiment yet built that can notice a single one. Then there is the material that outweighs everything ordinary. In the neighborhood of the Sun, dark matter is present at a density of roughly a proton's worth of mass in every few cubic centimeters. That is a small number in absolute terms, and it is nonetheless several times the local density of ordinary interstellar matter. In the space around us, right now, there is more dark matter than gas. It simply passes through the gas, and through the planet, and through everything on it, without any interaction we can detect. So the emptiness is thick with things. It is only empty of the particular kind of thing we are made of. And beneath all of that sits something deeper, which is that the vacuum itself has structure. Modern physics describes particles as excitations of underlying fields, disturbances in something that is present everywhere, whether or not any particle happens to exist at a given point. Those fields cannot be switched off. Even in their lowest possible state with no particles present at all, they do not sit perfectly still. They fluctuate, because perfect stillness would be a level of precision that quantum mechanics does not permit. This is not merely a way of speaking. It has consequences that can be measured in a laboratory. The energy levels of electrons in atoms are shifted by tiny amounts from where they would otherwise sit, because the electron is constantly interacting with the fluctuating vacuum around it. And if two flat, uncharged plates are brought very close together in a vacuum, they experience a faint attraction toward one another, arising from the difference between the fluctuations permitted in the narrow gap and those permitted outside it. Two neutral objects, in a perfect vacuum, with no charge and no field between them, are drawn together by the properties of nothing. A common way of describing this activity is to speak of pairs of particles briefly appearing and then annihilating one another again, borrowing energy from the vacuum and returning it immediately. It is a picture with limits, and it should not be taken too literally, but it captures something true. The vacuum is not inert. It is restless, at a very fine level, everywhere and permanently, and that restlessness is part of why the vacuum has the properties it does. The same restlessness is thought to have a remarkable consequence at the edge of a black hole. Near a horizon, the vacuum's behavior is affected by the extreme curvature of space, and the result is a very faint outward radiation, an object that famously allows nothing to escape, gently glowing anyway, because the emptiness immediately outside it is not truly empty. For any black hole of ordinary size, the effect is unimaginably slow, playing out over timescales that make the current age of the universe look brief. But it is there, and it means that even black holes are temporary, undone eventually by the properties of the nothing surrounding them. The vacuum has other properties as well, and they are among the most fundamental constants in physics. It is the vacuum that fixes the speed of light. It is the vacuum that sets the strength of electric and magnetic interactions. Empty space is not the absence of a medium. It is a medium with characteristics that everything else has to obey. There is a pleasing symmetry in this, reaching all the way back to the second part of the evening. We began by finding that an atom is almost entirely empty, and then had to add the qualification that it is empty of particles but full of field. Here, at the far end of the scale, the same qualification returns in the same form. The void is empty of particles and full of field. What separates the inside of an atom from the interior of a cosmic void is a factor of some 40 orders of magnitude in size and almost nothing at all in kind. Even the temperature is not zero. That ancient light supplies a floor of a little under 3 degrees above absolute zero, everywhere in the universe, which means absolute zero is not reachable anywhere in practice. The coldest place that could exist is still gently warmed by a light released before there were any stars. And then the largest fact of all, which is that the emptiness is increasing. Space is expanding. More than that, the expansion is accelerating, driven by something that behaves as though it is a property of volume itself. The more space there is, the more of this effect there is, and the more of it there is, the faster new space appears. It accounts for roughly 68% of the total content of the universe, and it is, as far as anyone can tell, a feature of emptiness rather than a thing sitting inside it, which produces a quiet conclusion. The amount of matter in the universe is not changing. The amount of space is. Whatever the ratio between nothing and something happens to be tonight, it was smaller yesterday, and it will be larger tomorrow, and it will go on growing without limit. The universe is not filling up. It is opening out. Given long enough, that opening becomes the whole story. As the expansion carries distant galaxies away faster and faster, their light will eventually be unable to reach us at all. One by one, over hundreds of billions of years, the galaxies outside our own bound group will pass beyond reach and fade from the sky. Eventually, the merged remnant of our galaxy and its neighbor will sit alone in a dark that contains nothing else observable, an island of stars in an emptiness with no visible far shore. Anyone looking out then would see exactly what the earliest astronomers assumed they were seeing, one system of stars and nothing beyond it. It is worth gathering the ladder one last time, because the descent has been long and the shape of it is the point. Air, at 25 quintillion particles per cubic centimeter. The finest laboratory vacuum, at about 1,000. The solar wind at the Earth, at 5. The space between the stars, at 1. The bubble the sun sits inside, at 1 in 20. The space between galaxies, at 1 in a million. And the interior of a void, thinner still. 25 orders of magnitude, from a lungful of ordinary air to the emptiest place that exists, and the last rung is where most of the universe lives. So here, at the end, is the correction the whole evening has been making. The pictures were never wrong about what is there. The planets are where they are drawn. The nebulae have the shapes they are given. The galaxies really do look like that. What the pictures could not show, and were never able to show, is how much of everything else there is between them. Every bright thing in every image is a local exception. Every star, every world, every stone, every hand, every page, each one is a place where the universe briefly gathered itself into something dense enough to be seen, against a background that is, overwhelmingly and almost everywhere, nothing at all. Matter is not the substance of the universe with gaps in it. The gaps are the universe, and matter is the rare and temporary decoration. This is not a diminishment. A thing does not become less remarkable for being rare. If anything, the arithmetic runs the other way. In a universe averaging 1 atom per 4 cubic meters, the existence of a place where atoms are packed at 10 to the 30th times that density, arranged into oceans and forests and warm rooms with people asleep in them, is a considerably more unlikely achievement than it appears from the inside. And there is nothing in that to be uneasy about. The emptiness is what gives the light somewhere to travel. It is what lets a galaxy turn without touching anything, what lets a comet fall for 1,000,000 years without meeting an obstacle, what allowed the atoms in your body to be scattered across a cloud 20 light-years wide before gravity drew them slowly together into something that could sit still on an evening like this one and think about it. There is room out there. An enormous, patient, unhurried amount of room, and it has never been in short supply, and it never will be. So let the sky be as empty as it is. The stars are further apart than any picture has ever shown, and they have been drifting quietly at those distances for billions of years without needing anyone to watch them do it. Let your breathing slow. Let the space around you feel wide and unhurried. Sleep well, and good night.